Welcome back. We've introduced the basic idea of the Z-transform, and we've also talked about convergence in the Z-transform a little bit. I'd like to switch gears and talk about some Z-transform pairs, and we can go through some of that development, and hopefully you'll get a little bit more familiar with the Z-transform itself. So I have a copy of the Z-transform definition written up there at the top of the page. And in the text, you can also see table 3.1 for a more complete group of Z-transform pairs. I actually have a reference book that was expensive. I bought it when I was in college thinking I would use it all the time. And right now it's a big thick thing. It's holding up somebody's monitor. Has been for years. It has an even larger Z-transform table in it. But I never used that. For the most part, these are the pairs that you worry about. The first is pretty easy to come about. We could see this by applying the definition of the Z-transform over all n is just going to be z to the negative n naught. Quite straightforward. And therefore, although this is a special case, that's just equal to 1. That's very nice to know. It's essentially the identity. What happens if you have a signal that is only non-zero between 0 and m minus 1? We can use the summation formula we developed on the previous lecture to give us 1 minus z to the negative 1 for this one. Now obviously for this we can't have z is equal to 0. That would be outside the region of convergence, because if z was equal to 0, z to the negative m would be infinity to the mth power. That's pretty bad. But if you ever get in an argument with a childhood friend, you can always say something about infinity to the mth power, and I'm sure you'll win the argument. Okay, so here we have the one we developed on the previous page. A related one, but not often used really, is this one. 1 minus a z to the negative 1 squared. And one of particular importance is cosine. Now with the cosine, remember we introduced the Z-transform to address convergence issues as one of the reasons. And since cosines are really important in LTI systems, being eigenfunctions of LTI systems, you would hope that the Z-transform would solve our convergence problems with cosines. And indeed it does not. Because if you choose z such that z to the negative n goes to 0, then as you move towards negative infinity, it will blow up to infinity. So that's not going to work either. So we have to we can do a cosine. We just have to make sure that it starts, it's right-sided. It's what we call it. In this case, it starts at 0. And this gives us a relatively strange expression. And there we are. Okay, I want to, in table 3.1, there are many more, but I want to make a few comments about some of the things you'll see in table 3.1. We will not be dealing with left-handed sequences in our discussion and in this class. But let's assume you had one. You would get something like negative a to the n u of negative n minus 1 is in table 3.1. And it transforms into 1 over 1 minus a z to the negative 1. So in this case, in the one to our left, in order for convergence, we have to have that a is less than z, or z equivalently is greater than a. But with this one, it's the other way around. Here we have a has to be greater than z. So your region of convergence depends on which direction you're going. And once again, it's because we're raising z to the negative power of n, and we want this quantity to decrease as we go towards infinity. But with a negative sequence, this one is a left-sided sequence, infinity means going towards negative n. And so in that case, we want z to go to 0 as it's raised to an infinite power. Essentially, we're going towards negative n, it's raised to the power of negative n, so the two negatives make a positive. When z is raised to n, we want it to go to 0, so it needs to be smaller than a. Accordingly, the region of convergence for a negative sequence, a left-sided sequence, is going to be inside, whereas the region of convergence for a right-sided sequence will be on the outside of A. And then the book goes into great detail saying, well, what happens if you have both left-sided and right-sided sequences? Then it's possible to get annular regions of convergence, donut-shaped regions of convergence, and things like that. In signal processing, we almost exclusively use right-sided sequences. And since we want convergence when the magnitude of z is equal to 1, so that we can include the DTFT in our analysis, we further have limitations like this. So, if you have specific questions about that, feel free to bring it up with me. I wanted to explain why we have these. There's such a great deal of discussion about region of convergence. This is basically it. In essence, the region of convergence cannot include a pole. A pole is where the Z-transform blows up. So one last point about regions of convergence. Let's assume we had a1 to the n, u to the n, or u of n, plus a2 to the n, u of n. Since the Z-transform is linear, just as the DTFT is linear, this would transform into 1 minus a1 z to the negative 1 plus 1 minus a2 z to the negative 1. And the region of convergence would have to take into account both a's. So in this case, the region of convergence is z has to be outside of a1. It also has to be outside of a2. So you might have a situation like this. where you have A1, A2, the region of convergence is outside of A2. And fortunately, the way I drew it, it also includes the unit circle. Okay, let's switch gears just a little bit and talk about some of the properties of the Z-transform. And in the text, this would be table 3.2. So assuming that we have x1, or sorry, x of n by the Z-transform goes to x of z. And we'll also assume that x1 of n transforms to x1 of z, and so on and so forth. So if we have our first major, very useful property is the linearity of the Z-transform, which is just what you might expect, like that. So the next one that's really important is a delay, since filters deal with signals at different delays. So this comes up all the time. This transforms pretty much just like the DTFT did. There it was e to the minus the j omega n naught. Here it's just z to the negative j omega n naught. One that's not used as often, but we saw where it was used up above in one of the examples, one of the pairs, or at least it can be used to derive that pair. It's if you take the derivative with respect to z and multiply by negative z, you get n times x of n minus 1. Two more properties, and then we'll show where some of these are developed and where they come from. This gives us x star, or conjugate, z conjugate, and then the granddaddy of all the properties is that x of n convolved with x1 of n convolved with x2 of n transforms into x1 of z times x2 of z. So anytime you can take convolution, a very complex operation, you know, a high computational load, and turn it into multiplication, that's a huge advantage. I will say right now, though, that unfortunately you really don't save much. It turns out if you're to multiply two large polynomials, you can get their coefficients of the result by convolving the coefficients of your two multiplicands. So really convolving by multiplying the Z-transform is essentially the same thing, but the same operation if you were to actually code it up. So let's run through just the development of a few of these. Maybe this one right here on delays. So if we were to take x n minus n naught, z to the minus n, and do a substitution of m is equal to n minus n naught, then the sum over all n is going to be the sum over all m. So we just change that. This is now x of m, and z to the minus, and now we have m plus n naught. Well, we can bring the z to the minus n naught out front, leaving us with the Z-transform of x. And so that's where that comes about. Now, because signals that are infinitely long in both directions, generally you won't converge if you try to take the Z-transform. So it's very common to see signals of the type like this, where we multiply it by u of n in the process. Another way to deal with that, and I'll put it up here with the other one, is just to define the unilateral Z-transform, and that is defined from n equals 0 to infinity of x of n z to the minus n. So if you hear talk of the unilateral Z-transform, essentially the Z-transform takes into its own hands ensuring that we have a left-sided sequence via that definition. Okay, I'm going to go through one more example. I think we might have to go on to the next page here. Actually, I bet we can fit it right here, just for convenience. So, let's take the Z-transform of x1 convolved with x2. So x1 convolved with x2 is going to be the sum over k, x1 of k times x2 n minus k. And the Z-transform of that would be the sum over n, z to the minus n stuck out front. Well, if we swap the order of summation, then we'll get the sum over k of x1 of k times the sum over n of x2 n minus k z to the minus n. Well, that's the Z-transform of a delayed version of x. And we know from right above what that would be. So this is just x2 of z times z to the minus k. So over here now we have the sum over k of x1 of k times z to the minus k x2 of z. But that sum is just x1 of z, giving us an almost trivial proof that the Z-transform of a convolution of two sequences is equal to the product of the Z-transforms.